morning, everyone. My name is Dave Creighton. I'm with Seagate Technology. I'm here with Joel Schipper. We are in the product planning organization, also known now as technical marketing. Today, we are going to talk about several technology breakthroughs in mass capacity storage, specifically hard drives. So here's the agenda. We're going to talk, a little bit first, just kind of a little upfront context about the scale of HDDs just in the data sphere, in the data center, and for AI. And then we're going to go into, one of the major topics, which is HAMR technology, which is the heat-assisted magnetic recording. And then we're going to talk about two other features, one around storage reliability and sustainability with the storage element depop. And then Joel is going to go through some details on optimizing performance with hard drives in the data center with the command duration limits and priority management features. All right, so how much data, right? The global data sphere, this is an IDC and a mix of number of different projections, but by 2028, the projection is that 394 zettabytes of data will be created. That is an enormous amount of data. I don't think I have to convince anyone here that there is just an absolute explosion for many different reasons in the amount of data being generated. Of course, not all of this is stored, but a lot of it will be, and we are growing how much we are capable of storing as we go into the future with these technologies that we're going to talk about. If we break down that data that does get stored into several different categories, I think the key thing to recognize is that most of this enterprise data really falls in the general purpose workloads. This is 80 to 90% of this data. You see this big circle here on the left. 80 to 90% of the overall data ultimately lands on magnetic storage with hard drives in the data center. If you look at sort of the y-axis here, this is just showing, right, the high capacity on the upper end of the y-axis, and then the x-axis is really how quickly do you need to access that data for various applications. Well, 90% of this is things like, object storage, large blob storage, and AI data retention, all the things that kind of come back that you want to save for later, whether it's, video or any number of other, business data that you need. And all your documents, that's 90% of it, but you don't need it very quickly, and this is where it lands on hard drives, right, warm and cold storage. Then about 10% of that data is really this transactional, right, database type storage where you need sort of this real-time data transfer. This is where you might see start to see more and more flash, more and more, faster storage devices. And then as you get into the ultra real-time data transfer, this is your AI and machine learning training data that gets put into both flash and in DRAM. All of the, real-time graphics, your scientific simulations, all of these types of things that you need, sequencing data, this type of thing. But this only makes up about 1% of the overall data that gets stored in data centers. So when we talk about AI and what that data looks like, right? So on the far right here, you're looking at the majority of the data being stored on really your network hard drives, your storage clusters, right? And then as you move closer and closer to the sun of the GPUs where you actually need to saturate, right, you have your network SSDs, and then you go into and move into your compute cluster where you have the local SSDs and all of your DRAM, right? And these things then feed into your CPU, GPU, and all of that. But the point here is that all of this data ultimately starts and ends on mass capacity storage, which is hard drives. So whether you have your very large training data sets, your raw data, or your AI data retention, and all of these things ultimately land on hard drives where you really are looking for megabyte per second performance in a multi-exabyte scale rather than petabyte performance on the scale of terabytes. And so you might ask, well, why not just go all to flash, right? I think the big thing to recognize here about why HDDs and why the innovations that we're going to talk about are so critical to managing that scale of data is that replacing all of the exabytes that currently land on HDDs today with flash is cost prohibitive, right? For a number of different reasons, not just because of flash prices being 4 to 6x dollar per terabyte versus magnetic storage with hard drives, but also because we can't manufacture that much flash, right? So in 2023, 333 exabytes of NAND flash was manufactured. We estimate by 2027, about 963 exabytes will be manufactured in order to make up the gap between what is stored, what will be manufactured on HDDs and stored on HDDs. With flash, there is a huge missing chunk, which is this 2,700 exabytes of production that would be needed, right? And ultimately, in order to invest in those fabs, in order to actually manufacture that much flash, it's not a great return on investment for that scale. And so really what we've landed on and have had in the past and will have for the coming decades is this bifurcation of your IOPS density storage of SSDs and then your exabyte scale mass capacity storage with HDDs. And where we're going to focus today is on sort of this top line of the hard drives. We're going to focus on this new technology of HAMR. This is the heat-assisted magnetic recording. And this is really where we go from sort of the petering out of PMR technology and jump onto the next areal density curve. And we're going to talk a little bit about how that technology works and why it enables the scale and the new areal density growth curves that we are getting with HDDs. Okay? All right. So first, a little bit of background. Recognize not everyone is an expert on what makes up a hard drive, and so I'm going to kind of walk through just a baseline of what are the primary components of the hard drive, and then which areas are the key areas of innovation for HAMR technology. So first, when you are building a recording head, right, we manufacture these in wafer fabs. You build a lot of recording heads on a single wafer, and then you chop them up into bars, which is basically just a row of these sliders, which is an individual recording head. These are extremely small devices, but they contain all of the reading and writing elements, your write pull, all of the magnetic components that actually do that operation on the media. You then put the slider onto an HGA or a head gimbal assembly, and you can see kind of at the very end of the gimbal is where you put the individual recording head. You stack those up into a head stack, and then you have each one on each surface of the media, you have a recording head, right? And then those are interleaved in between the discs. And then you have the discs, the magnetic media themselves, right? You package all of those things up, add your electronics, your magnets, your motors, all of those things into the hard drive case, and then you have your hard drive. Well, with HAMR, the two areas of innovation that we're going to focus in on are on the wafer side. So what elements do you change in the recording head structures? And what type of material science innovation is needed for the new type of media? Because this is a very different type of recording technology that has different magnetic properties. And we're going to dig into why that enables such a huge growth in storage capacity. Okay. So all of this HAMR technology is in service of getting this additional areal density, right? And just as a reminder, the areal density is just bits per square inch. How many bits can we fit onto the magnetic media? Those areal density is composed of both the linear density, how many bits per inch can you get in the downtrack direction? So in other words, how small can you make those magnetic grains? And then you multiply that by the track density. How closely together can you squeeze those tracks? And those two together make up what we call areal density. So when we talk about new areal density growth, this is what we're referring to. We're referring to just how much can you pack onto an individual disk. Okay, so why is it so difficult to make this higher and higher density device? Well, the big challenge with growing capacity comes down to, in order to get that increased density, you have to make the bits smaller and smaller. But when you make the bits smaller and smaller, you wind up with significantly less thermal stability. which means that you have this higher and higher probability of the bits flipping and not staying stable after you've applied your magnetic field and sort of locked those bits into place. And this is a really significant challenge. When we think about PMR technology, what we've had over the last decade or two of HDD recording technologies, we've sort of met that limit, that threshold, right? We've done all these tricks in order to get additional capacity, but ultimately you meet a level of restriction from a physics standpoint, right? We've made these grains so small that we've sort of reached that limit. And so what do you do in order to continue the growth of capacity where we've been able to sort of double the capacity in the past? It has taken us almost a decade to double the capacity over the most recent products, but when we move into HAMR technology, we're going to be able to double every couple of years. So this is every 3 or 4 years. How do we do that when we've run into this challenge of the thermal stability of this really small bit size? Well, the solution that Seagate and others have been developing is called HAMR. So this is heat-assisted magnetic recording. And there's really two areas that we have to innovate in order to make this happen. I want to call your attention to this chart on the left here. So what you're looking at is on the y-axis, this is what we call coercivity. This is magnetic hardness. So this is how difficult is it to apply a magnetic field and actually have it flip the bits on the media, right? Well, on the x-axis is your temperature, and this green zone that you're seeing at the bottom is the writable zone, right? So when you're in the green, you can actually apply a magnetic field to those bits, and they will flip and change and store your data. If you're outside of this zone, applying a magnetic field does not flip the bits, right? And so the way that HAMR works, you can see up in the top left, the HAMR media is stored, when you have your bits stored, this is well outside of this green zone. If you apply a magnetic field in this state, you are not going to be able to change the bits. You have to first heat the media. That heating softens the magnetic hardness of the media and puts you back down into this green zone of writability. So then you heat the media, you can follow the red arrow, you heat the media, you wind up in the green zone, you apply your write field, you flip the bits, and then as you continue on flying over other bits, that media cools down very quickly and is sort of locked in place, sort of frozen in place, and no longer writable. And so this really comes along with one of the key areas of material science innovation with one of the hardest, magnetically hard materials that we know of, with an iron platinum superlattice. This gives us an incredible amount of thermal stability, and it has this property where you can soften it by heating it to a very high temperature, and then it cools very rapidly to go back to this state of high coercivity. So once you have this media, you need something that is able to apply that heat in a very focused, narrow zone and heat extremely quickly and cool very quickly. And so how do we achieve this? This is with the new head technology. What we've done is we've taken a traditional PMR recording head. We have added a couple of elements to it. There are really three kind of key elements that we've added to that recording head. The first is a laser. So this is an extremely small laser that is built into the recording head or onto the recording head. That goes through an optical waveguide and then into one of the other key areas of innovation, which is this NFT, or near field transducer. And we'll show a little image on the next slide about what that looks like. But essentially what this does, these elements together, takes the laser light through the waveguide onto the NFT, and then further focuses that light into an extremely small heat dot on the media. When that heat dot is applied, it heats up to hundreds of degrees Celsius really, really quickly. This is on the order of nanoseconds. It heats that media, softens the magnetic hardness. You apply the right pole as you fly through that heated spot, and then it cools down in a matter of nanoseconds. So all of this happens. I think the fun analogy that I've heard, this is like an Airbus flying at full cruising, speed over about an inch off the ground and shooting a laser at every blade of grass. That's essentially what is going on here from a scale perspective. The speed that you're flying over the disk, the speed that you're shooting the laser, and the heating and cooling that's going on. So it is really incredible technology to be able to do this, and it's taken us almost 2 decades to get here. On the right side, you can kind of see the structures here, right? So on the far right, you see the reader element. This is very similar to what you would see in a PMR device, and then you can kind of see those extra elements with the waveguide, and then your write pole on the far left there. And you can see the little heated spot on the media really is just the area that you want to write. Okay. So if we dig in a little bit more to these structures that enable this technology, on the left is sort of a cartoon view of the media layers. This is like a cross-section view. So you have your recording layer. This is your iron platinum lattice structure that has this new high coercivity or high anisotropy media with the different thermal properties than what you might see in traditional media. Then you have some interlayer material, and then you have a heat sink. So this helps dissipate all that heat off of the media, and then you have your substrate. And if you look at these 3 different images, you can see the bottom section of the image is a top-down SEM view of the individual bits or grains, magnetic grains on the media. And there's a little bar on the top that shows a cross-section of the size of those bits. And you can see from 2015 into now and into what is being developed right now, that the grain size is really significantly shrinking. And this gives you obviously this massive capacity benefit in areal density. The bottom is one of the key elements that's on the recording head. This is the near field transducer that I mentioned, the NFT. The light will hit this, the top of this near field transducer, and what it does is it further focuses that light into a subdiffraction spot onto the media so that you can heat only the part that you want to write. So what does this get us? Well, over the last several decades going back, this chart even goes before the year 2000 when we had longitudinal recording. The y-axis here is all about areal density, how much bits per square inch can you fit onto magnetic media, and then you sort of show the progression over the timeline of different technologies. And you can look back to 2008, 2009, when Seagate started developing and first showing in lab demos the first generation of HAMR designs. As we move further and further, you can see other variations and just the progression that we've been able to get to and accelerate the overall areal density that we're capable of. And the black line is sort of what the industry has been shipping for a very long time. This is perpendicular recording, and you can kind of see that back in 2016, that growth curve starts to kind of taper off, right? We hit some roadblocks in the physics that I mentioned, and so we really need to jump to this new technology of heat-assisted magnetic recording. In between these different designs, really that represents really key reliability innovations that we've made, different structures, different geometries, all these things in order to bring this concept into a mature product that can actually meet enterprise reliability specifications. And we've not only achieved that, but been able to demonstrate upwards in a drive, an actual built manufactured drive, 4 terabyte per disk. Right now, we're shipping 3 terabyte per disk. And so you can see that obviously puts us on a completely different growth curve than where perpendicular is taking us. We also have demos that can achieve up to 6 terabyte per disk. This is more not in drive, but on spin stand, right? Optimized, pieces in order to just demonstrate the viability, long-term viability of the technology. And we also utilize SMR. Now, I want to make a comment about SMR when it comes to HAMR. SMR today, you might look at something like 15, 20% additional capacity from doing that shingling from your media, right? When it comes to HAMR, regardless of supplier, that does shrink down. And where does that capacity go? Well, it goes over to CMR too. So with HAMR, you're able to squeeze the tracks and get that smaller and smaller bit density so small that you actually can achieve the additional capacity on CMR. And so that percentage shrinks to something like 10% or less. And we expect that to be the case regardless of which supplier is developing HAMR. And that just comes down to the actual recording geometry of how the HAMR technology works. And so we expect that to continue into the future. So you need to consider whether that tax of sequentializing your data in order to utilize SMR media is worth, that, 10% or sub 10%. It might be in some cases, and many people are using that. Just want to point out that we do pull a lot of that benefit over into a CMR device as well when we get to these HAMR products. HAMR, I guess one other comment is that this technology does not require, unlike SMR, it does not require any additional software or anything else at the host level. This is truly plug and play. You can take a fully enterprise reliable HAMR HDD and plug it in exactly like you would an HDD today. So that is a huge benefit. We get that additional capacity and the roadmap that comes along with it just by moving into this technology. That, again, has taken us almost 2 decades to develop. So how far can we take it, right? So right now we have several different models to evaluate advanced designs that are coming several years from now. We have several that we've identified that achieve it. I know it's a little hard to see here, but this is in the sub sort of 5 terabyte per disk that we've already modeled, and then there's additional advanced designs that are in both internal and external research that can achieve over 6 terabyte per disk. And we actually believe that if we look into the future, 10 terabyte per disk is achievable with HAMR and other component innovations. Now, we're not there today, but we are significantly further beyond where PMR is capable. We've achieved well over 5 terabyte per disk on spin stand. I think on that last slide, we were showing even north of 6 terabyte per disk. And we are already capable of doing 4 terabyte per disk in a fully formatted drive and fully built drive with HAMR. So this is all to say that HAMR really is the future of HDD technology. I hope you learned something about how this recording technology works and just sort of how bright the future looks of HDD storage and really how it's going to help us enable that massive data growth that we talked about, because ultimately 80 to 9% of that data gets stored on hard drives. Okay. So now we're going to switch gears and talk a little bit about the storage reliability and sustainability innovation. Now, I talked a little bit about storage reliability and how these HAMR devices really are exactly like an enterprise reliability HDD. And what does that look like? So just to kind of remind everyone, standard enterprise HDD reliability is a 2.5 million MTBF, or mean time between failure device. This translates to a 0.35% annual failure rate of HDDs over its 5-year warranty period of 24/7 operation. That's about 1.75% cumulative failure rate. Now, this feature that I want to talk about, it's really important to note that about 40% of those failures out of this cumulative 1.75%, 40% of these are just single head type failures. So this is where only one of your heads, one of your surfaces goes down. That means that 95% of your capacity, if you assume that we're talking about a standard 10 disk HDD, there's 20 heads, right? One for each surface of the disk. That means that 95% of your capacity is still good. Well, we are shredding millions of hard drives today because one head or one surface is bad, which means that we're getting rid of 95% good capacity, just throwing it in the trash, right? We don't want to continue doing that. And so there are other better ways, and I want to talk about storage element depopulation, or drive regeneration, as we call it. This is a standard feature that several hard drives that are shipping today are capable of, not just with HAMR, but with PMR products. And with replacing these hard drives costing thousands of dollars for technicians and pulling the drive, and not to mention the most important thing, which is your storage availability in your data center. Just to give an example, right? If you have, let's say you have a 95% storage availability target, right? That's 5% of your storage that you're planning for being down at any given time. Well, if 40% of those failures are eligible for bringing the drive back online with a slightly lower capacity, which is what this feature is all about, that's 2% of your data center that you're getting back, right? You're getting a massive amount of storage back that you didn't need to shred in the first place. And so this is really, really significant, not just from a storage reliability and availability standpoint, but also from a sustainability standpoint. We don't want to be shredding all of these drives. The best thing we can do is continue to use them, not just, for their entire 5-year life, but even beyond, right? Many drives can last even beyond that, and we want to enable these drives to run as long as possible. I don't have it here on the slide, but if you compare reusing the drive or continuing to use the drive, even to recycling its components, it's 275 times better from a carbon footprint standpoint to continue to reuse the drive than recycle. That is a massive sustainability benefit, and I think we can all agree that there's something that if it's possible to continue to use that capacity, we should do everything we can to try and continue using it. So I'm going to dig in a little bit about how this process works. Many of you may be familiar with this, but just as a really high level, this feature is known as storage element depopulation. It allows the removal of a single head and surface from the usable LBA space. So if you look at the flow chart here, it's very simplified, and we'll go a little bit more detail here. Let's say you have a 20-head drive that's fully online, fully operational, working normally. Then you have an actual or predicted head failure, right? Whether you predict it at a system level from your parametrics, or the drive predicts it itself and alerts the host. You can then, depending on whether you have a CMR or SMR device, there are a couple of different options that I'll go into. The drive goes through a process of being re-provisioned, and then it's reintroduced with a new LBA space at 19 heads online, or 95% of its original capacity. So again, most of that capacity is still good, and we find that if you have a single head failure, many of those, almost all of those in fact, do not continue to have additional failures just because you had one head go bad. Okay, so there are two types that you may have seen in that flow chart, and one at the very top, we have what's called standard offline regen, or remove element and truncate is the command that you can issue to the drive. This function essentially tells the drive to do a full format and re-provision the LBA space to a slightly lower capacity. In the ecosystem, this is already supported and in use in Linux and on HDDs today, so you can already take advantage of this. Now, there are some downsides with having to, take the drive offline and go through a full reformat, right? That does take time. Now, it's not as bad as having to, schedule the drive for removal and then replace it and then use up some of the spares that you have. But it does take some time in order to go through that process. And so there is another option if you have a zone block device, which is the online regen, which is called remove element and modify zones. The advantage that we take, we take advantage of the zone block functionality by removing just the zones that apply to that single head or single surface that has gone bad. This does leave the good data intact, so you don't have to go through a full reformat. The zones with the failed heads are then marked offline, and then you kind of bring the drive back again with a slightly lower usable LBA space. This is also supported in Linux on SMR-only HDDs today. And then there's one more that I want to point out. This is the LBA status log. This is something that's in development right now that has been defined in standards. This essentially is a rolling log that the host can access that says which LBAs are good and which ones fall under sort of this failed surface or failed section of HBAs. And it allows you to essentially have the flexibility to to continue to use the good LBAs and go through either a plan for your rebuild before you go through this remove element and truncate. And there are a number of other things that are in sort of the concept phase to allow other options for online regeneration, but these ones are really the ones that are defined and in use, either in use today or in development and coming soon. Okay, so just a little bit more detail about how you use this. So, of course, the first thing to do is confirm that the drive supports it. And then once you confirm that, the expectation is that the enterprise HDDs have internal algorithms that monitor head health metrics and can actually tell the host when the head is either failed or is predicted to be failed. In order to check that health status, you have the get physical element status. This field notifies you on a per head basis whether or not that head is eligible for this depop process. And then, of course, the host can decide whether or not to regularly poll that, or there's also another option in the device statistics notification page that will give an alert when a head is predicted to either be failed or about to fail. And you can watch that device statistics notification physical element status changed field. And then after that, you decide whether or not you want to depopulate a head. So after that's been identified, then you can issue, for example, the remove element and truncate for offline regen, poll the device for an estimated time of completion for the operation, and then after that completes, you can then again check the get physical element status by head, and you can receive that status back. FF means that a successful depopulation has occurred, and then the drive comes back at its slightly lower capacity, usable capacity, but it is fully functional and operating normally 95% capacity. The drive reprovisioning does change the capacity, obviously, so in a hardware RAID setting, this is a challenge, right? And so there's nobody using this with hardware RAID today, but those that can utilize, other types of redundancy schemes, erasure coding, and that, some of them already are using this feature. We use it in the Seagate systems, for example, and several of our customers also use this already, many of you. And so it's already there in the features, ready to be used. So if you want to reclaim, some of that capacity, there is now an option to do that. Okay. So now I'm going to hand it over to Joel Schipper, and he's going to talk about optimizing performance with the CDL feature set.
All right, so I woke up this morning, I was just feeling a lot of gratitude for the storage development industry as a whole, just kind of realizing what it takes for features like this, hardware all to come together, conceptual from an idea that starts on a whiteboard and then ends up in standards bodies, gets defined and creates deterministic outcomes among vendors to get to these points. And as that then gets integrated into our hardware and products, it's pretty amazing. Then it has to flow into the stack and into the operating system layers to make these things actually usable to the end users and customers. So as we get into optimizing performance here, I just kind of wanted to lead in with that. And so I thank you all for your investment and patience and persistence in this industry. Let's see, Dave, just the arrow here. So, as we give more flexibility in command selection to the hard drive, we have to look at how latency and throughput is affected, and it becomes critical here as we look at that. So, an approachable way to look at this is an intersection here with a traffic light at a busy intersection. So here you can see that moving east-west, you can imagine we have a high throughput traffic here moving, heavy traffic that represents high throughput. And then from the south, we see a car approaching, the infamous red car, little old lady from Pasadena. She's waiting there at the light. So the light has to make a decision when to halt the busy traffic and allow that car through. It can't hold her there indefinitely. And At some point, it has to stop that at the opportunity cost of reducing the overall throughput that the intersection can handle. So as that light changes, a penalty is paid there. Next, we observe here, as an example, a high priority read command, which could be analogous to a emergency vehicle that approaches the intersection. And as it comes closer to the intersection, the relative priority of that high priority read command imposes a cost to all the other traffic at the intersection in latency and throughput. But given the latency needs of that high priority read or the emergency vehicle, that penalty or trade has to occur. So as we biggie size our storage, as Dave talked about here, we see more customers, applications, users per spindle, and that brings more priority on increasing efficient use of storage in performance. So the command duration feature set allows the host to impose time limits on read and write commands, and if those time limits are not achieved, it gives an action, associated action of outcome that the host imposes on the drive if that can't be met. So one of the opportunities that exists with this is the ability to have different classes of I/O, and by doing that, we can also establish areas where we want to be able to increase queue depth on other commands. In the past, we've seen limitations on this, other feature sets that have been defined, and then systems and the industry imposing just limiting queue depth to control the overall tail latencies that are required to meet the service level agreements customers have. Some of the downside to limiting that host queue depth is that the commands age on the host rather than the drive, and it gives up an opportunity cost of throughput there. Another feature that's been leveraged in the past is the NCQ priority feature set. This was an ability to provide a relative priority status, but it didn't confer the weight or significance. You couldn't separate significance and read and write. It was pretty ambiguous. Trying to think of an example here. I was reading that the word love is your junk drawer in your kitchen kind of a word, because it can mean everything and nothing at the same time. So that's kind of how the NCQ Prio feature worked for most, and it was not very deterministic among other vendors. As we move forward with the command duration limits feature set, which was actually defined, I think, about 5 years ago in standards bodies, I see some of the members here today, it's evolved into clarifications as this iterative process has occurred with this feature set to make it more effective and deterministic among the vendors. It allows you to specify duration limit descriptors, 7 for reads and 7 for write commands. These descriptors allow you to specify 3 different time domains, as well as the DLD policy actions to take if those time limits and those time domains are not serviceable by the drive. To start with, we have the inactive, the active, and the total time periods here. The inactive time is the time that the command spends in the drive's queue and is waiting and could be bypassed multiple times before it's actually serviced. The active time is the time the drive spends actually transferring the data to disk or retrieving it from the disk. The total time is the time from the initial acceptance of the command to the final command status. So this helps the host have a way to convey to the drive a hint to the sensitivity of these commands. And it allows a mix of commands, so it can be very effective. So what happens if the drive can't meet the latency? So this is where the duration limit policies come into place, And some of these have changed just recently in this year in the standards bodies with the collaboration of multiple companies. The first one here, policy 3, is the continue limited. So if I don't meet the time that was specified, for example, in the inactive time period, and my policy was continue limited, this gives me the option to move to the next duration limit index and apply a new time limit and a new policy. So this is effective if you want to push out a command. I asked for it to be serviced in 250 milliseconds, but I'm willing to allow it to push out another 100 milliseconds and apply a different policy. The next is the best effort policy. This is kind of I want to talk about me policy. It's going to sacrifice the needs of other latency needs and throughput of other commands to get this command executed. The next one is continue unlimited. This is basically saying don't penalize other commands. You can push this command out almost indefinitely. The next policy is policy D, which is an early return without error. This predominantly came out of the OCP fast fail. So if you're reading up multiple shards and you want to limit the time on, you only need 10 or 15 shards to reconstruct your data, you can give up early on some of these and be sometimes faster to get your data from another location. And then the last one, policy, the other benefit with policy D is it doesn't blow away your queue. So as I return early, it doesn't abort all the other commands in the queue, like when we get errors typically, especially in SATA. The last one, policy F, is the big sledgehammer. It does return early at the time limit, and it does impose an error and blow away the queue. Let's see. So I'll conclude with a little example of actual measured data here. Here I use 2 duration limit descriptors to shape the tail latencies of 2 simultaneously ran jobs. And then I varied the queue depth to increase the overall throughput. So to start out with, I had a baseline there in blue, which is 4K random read, 8Q IOPS, which is approximately 141 IOPS. You can see down on the bottom chart, this is latency in seconds. And that overall out to 4 nines moving toward the right there stayed just went a little bit above 200 milliseconds. So now I started to add in the 2 simultaneous jobs, and this time actually applying CDL limits. So for the low priority command set, I ran that with 4K 8Q with a 250 millisecond duration limit timer and in the inactive time domain with a best effort policy. And then I ran simultaneously another 8K for 4K 8Q workload with a 2-second timer to work in some additional background workload. So essentially the drive's getting a queue depth of 16 at this point, but these workloads are ran simultaneously. So overall I'm able to increase the throughput of the primary low latency workload and add in additional background workload. As you can see on the bottom chart, the solid line is the low latency workload, which stays flat at the 250 milliseconds that I established in the duration limit descriptor for the low latency workload. The high latency workload, which has a duration limit out to 2 seconds, starts to creep up and goes just above 1 second there at the 4 nines. The next one, I added in an additional 8Q on the primary low latency workload at 250 millisecond for the duration limit descriptor. And you can see that the IOPS did increase while the latency remained flat at my 250 millisecond time limit. The background workload does start to creep up more as I add additional queue here. You can see that starts to creep up at the 4 nines closer to the 2-second limit, but doesn't get all the way there. And then the last example here that I ran was maxing out the SATA queue depth here on this drive at 32. running 24Q for the low latency commands and maintaining a nice low 250 milliseconds out to the 4 nines, and adding in a little additional workload. In this case, you can see the top green line with the white bullets. It does start to just creep at 4 nines, slightly above 2 seconds. My next slide, I did add in what happens if you don't use duration limit descriptors. So while I was able to continuously increase the queue depth and gain overall throughput by 5 to 15% in the highest queue cases, you can see that the latency spreads evenly and it doesn't have any control for mixed workloads. If nothing's a priority, everything's a priority, nothing's a priority. So that's the end of that section. Dave, did you want to come up and address the key takeaways here? I'm seeing the sign flash at me.
Okay. All right, so just to kind of recap key takeaways, right? So we talked about the data sphere growth and, how HDDs are storing about 80 to 90% of the bytes. That will, is the case now and will continue to be in the future. HAMR technology is really how we significantly accelerate and extend that areal density growth in order to meet that storage demand. We talked about the regen or storage to population features, and I just want to, that's the call to action, right? If you can utilize that, I think there's a huge opportunity to improve storage availability and sustainability of HDDs in the data center. And then Joel talked about the command duration limits enabling the higher queue depths and giving us really the flexibility to manage different classes of I/O. So with that, I'll open it up to questions. It looks like we just have a few minutes for questions. Yeah, go ahead. Yeah, we aren't showing the data here, but we have looked at that extensively. It is extremely unlikely when we have the case where, the 40% that I mentioned of failures being eligible for this single head, of those 40% of failures that have that single head, almost none are then followed with additional head failures, right? If it was truly eligible for that single head regeneration, it is very unlikely that a second head will be, right? That 60% bucket, of course, are things that kind of apply to the whole drive as a whole, right? Let's say it's contaminated or your motor goes bad or whatever other types of failures that you have. That's sort of the 60% bucket. But it is what we see is it's extremely unlikely. You are able to have a second head be depopped, right? So we allow up to 2. And in that case, your overall reliability or overall failure rate for your population of drives goes way, way down. I mean, it is a huge benefit to the overall reliability in your data center. So we allow up to 2, but it's very rare that we see a second one. Yeah. Okay. Yeah, the question is, the overall percentage capacity gain that you get from SMR. I mentioned that it's about 10% or sub 10% when you get to HAMR, because a lot of that gets claimed by the overall system with CMR as well. And the question is, do we see that percentage dropping? I think over time we will see it drop slightly. I think there will always be some benefit to shingling the media, and there are those that can take advantage of it and optimize for that at scale will continue to see benefit, and we see that going forward. I just don't think that it's going to go back over 10%. I mean, think between 5 and 8%. I think very long term is about what we see.
Yeah, if I could just ask a little bit more on the question about the second head failure following the first head.
Sure. Right. Right.
enough drives that have gone into an environment with deep pop, you've got statistically significant data on that second head?
Sure. So I think one thing that might help clarify, right? When we say that a failure is eligible or a head is eligible for regen, for successful regen, I think that's doing a lot of heavy lifting, right? So there are scenarios where you may have, let's say you have a contamination in a drive, right? If that drive is very contaminated, you may have a high probability of many things going wrong because eventually those particles, can contact multiple different heads. But typically what we see is that over the drives that are, in use for a long time, right? If you sort of take out that initial set of drives that have that type of failure and that run in the data center for let's say a couple of years, and then you have a single head, those types of failures are typically not the type that affect multiple heads, right? You have like a single head that has degraded over time rather than something like contamination. And in that case, it is really a statistical event of that individual head rather than something that is applicable to the entire drive. Yeah.
Is there any impact on power consumption on the drive with the HAMR?
With HAMR. So it's fairly minimal. I mean, we're talking the overall average power probably on the order of 100, 200 milliwatts, right? It really depends on the type of workload though, right? So you may have some, overall the drive subsystem may have compensated for that additional power in certain areas in sequential, right? Whereas you may have slight increases in other types of I/O, but in general, the overall power is not significantly increased, and we continue to make those generational improvements on overall power.
You mentioned that you have two different methods of doing this. One allows or requires a reformat, and the other one carries a little bit of cost associated with it, but avoids a reformat. What's the relative interest that you find between those two?
So the question is, what's the relative interest between the two different types of drive to population? So one, yes, you're absolutely right. There is a penalty to pay with the reformatting, right? So I would say there is what we see, at least at Seagate, is that there is a small number of high volume customers that do like to take advantage of not having to reformat and using this other type with the SMR. Generally, though, there are a lot of other issues, right, that come with some architectures in taking advantage of, and paying that sort of system-level tax in using SMR. And so there's, in Seagate systems, for example, we take advantage of this ability to do this depopulation and reformat just by having an overall storage box that has enough to sort of manage through erasure coding, taking those drives offline and can continue operating at its full, redundancy and sort of manage through that. So I think the answer really is just if you have the scale and you have the right redundancy scheme in place, you can manage that overall. But to your question of relative interest, it's both, and it depends on the architecture that's being used. Yeah, right here.
This is a question that I'm an SSD guy, not an HDD guy, so maybe the lingo's the same. We have workload limits defined typically as terabytes written. Do you guys have that, and will HAMR have that?
So the question is about terabytes written. So one important point that I didn't mention is a really good question. So when it comes to reliability in a hard drive sense, it is not entirely analogous to like a wear-out mechanism. What we see is that it's much more like probabilistic failures when it comes to, like, when we're talking about whether a head is eligible for regeneration or these types of failure rates. It's not that they're wearing out in that sense, so it is a little bit different. But the way that you solve when things do go wrong is fairly similar, right? You can either over provision at a system level rather than a device level, but it is not entirely analogous. We do have a overall how much workload per head. We have the ability to track those statistics, and those are actually available in what we call our farm log So these are things where the host can pull these device statistics and look at these things on a per head basis. And it is important to track that workload. And we've published for decades the overall terabytes per year specifications, right? But it is less of a wear out mechanism than it is just the overall reliability probabilistically.
So it's something like a terabytes written, but more complicated, obviously, for your specific.
Yeah.
The fact that these drives are going to get meaningfully more dense, and you're going to have to adjust that sort of thing.
We are, and in fact, we are looking at increasing the overall, because what we see is that as drives go up in capacity, they get used more, right? I mean, you have to pass more terabytes in order to utilize and not have that stranded storage. And so we've been working very hard to try to actually increase at a small amount, but increase the overall allowed terabytes written. But at the end of the day, the more that you utilize the drive, the more data that you pass through, the higher chance you have to fail, right? Yeah. How are we doing on time?
The next session starts at 10:35, so you have about 10 minutes.
Okay.
But you want to give
Okay, we'll wrap it up. Just maybe one or two more questions. Okay. Any other? Yeah, go ahead.
Just following on from that same question, obviously in Flash you've got the FTL that's doing sort of low wear balancing. Media, there's no such.
Yeah, so the question is, on SSDs we have this concept of sort of wear leveling and over provisioning and these things in order to manage that. Do we have that on HDDs? Typically what we do on HDDs is we offer up the whole formatted capacity, right? We don't over provision, for example, and have spare heads within an individual drive. It's something that we've thought about, and I can't say never, but right now we do not do that sort of individual over provisioning or wear leveling in the drive itself. We do pay very close attention to the amount of background activity and the amount of sort of write amplification that we're doing at a drive level in order to make sure that we're not overusing those heads in the background with things that aren't host I/O, for example, but we don't do the exact same as you might see in SSDs. Good question.
I didn't mean at the head level, I meant sort of an individual bit on the drive. Where if you're writing the same sector again and again, and there's no reallocation.
Sure. Yeah, so we're talking about at an individual bit level, if you're constantly writing the same bits, right? Do you have this concept? Yeah, and actually there's two ways that happens, right? One is you have a layer of lube on the disk. If you're constantly flying over that, right, you can wear that down or actually spread it out, right? And so we do have protections in the drive, and this isn't just applicable to HAMR. This is all HDDs, right? So we can move the heads around in order to sort of level out that lube layer. The other is just magnetically, right? If you're constantly writing to one area of the disk, you can have some adjacent track interference, right, where that write can affect others if you're constantly hitting it. And we have protections in place. We have a feature called DOS. And this is, across the industry, there are DOS algorithms or directed offline scan where you actually move, away or replenish areas that may be affected because they're right next to where you're constantly hitting the drive. Right. And typically there's thresholds in place to sort of monitor on an LBA basis whether or not you're hitting that area too hard and you need to go off and fix it or at least make sure that it's still good. Yeah.
So, do you predict as your density grows that your bandwidth will follow up, or are you going to level out second limit per day?
So the question is, as the capacity grows, what do we expect to see when it comes to bandwidth, right, or IOPS per terabyte, right, is one way of looking at it. You do get some additional performance from the BPI growth, your bits per inch growth that you get when you shrink the grains. But ultimately what we see is that the capacity is outscaling the performance, right? And so that's why this idea of stranded capacity and IOPS per terabyte is so critical to watch. And it's something that we've tried to we've tried to solve with various other technologies like dual actuator, adding an additional actuator, right? I would say that, that essentially doubles your IOPS per terabyte. It's like 1.9x on drives that we're shipping today. And some have been able to take advantage of that. But again, we're growing capacity so quickly that there are other areas at the host level that have been managing through that. And so we see it sort of slowly creeping down and from an IOPS per terabyte perspective. But there are other options to manage it. Good question. Okay, I think that's probably all we have time for. So thank you very much. Appreciate the time.